Good afternoon, everyone. My name is Ryan Reynolds.
I'm Jared Vogt.
And this is the VR MIPS ISA. So just a brief overview of what we're going to cover. We're going to cover the MIPS ISA, the memory structure, the processor register set, the data types, the addressing modes, the instruction formats, some enhancements we did, the hardware schematics, our implementation and operation, and then a little bit about our verification methodology and some examples. So let's get right into it. The memory structure, we did a Harvard memory architecture, and so that allows parallelism and us to access different memories. We had 32-bit memory addresses, which allows us to have about 4 billion accessible locations. And then for our implemented memories, we did 4K by 8-bit, which essentially equates to 32 by 1K memory. And that's big endian format, so the most significant bit of data is stored at the least significant bit of memory address. For our processor register sets, we had 32 separate 32 general purpose registers. Some special registers that are important are R0, which is always has a value of 0, register 29, which is the stack pointer and will have 3 FC, and then register 31 is our return address for a jump and link. Then we also had 3 additional 32-bit pipeline registers in the data path that were for the multi-cycle instruction, and also we looked into pipelining a little bit, but we didn't actually implement it. We have a 32-bit program counter and instruction registers, and then 5 separate 1-bit ALU flag registers, which are stored in the control unit, and those are 0, overflow, carry, negative, and are interrupt enabled.
That one's not from the ALU.
Oh. So for our reset, following a reset, we're going to have all the CPU registers set to 0, the PC is set to 0, and then our ALU out will get 3 FC, which will set the stack pointer, R29, in the clock after a reset to 3 FC. So we had 2 data types. All our data types are 32 bits, unsigned and signed. Unsigned has values from 0 to about 4 billion. Signed has values from negative 2 billion to about 2 billion, and by default, all of our operations are going to be signed unless it's specified by the instruction. For example, an add unsigned would then use the unsigned data type. So our addressing modes, we have 3 of them: register direct, immediate, and register indirect. Register direct uses processor registers as operands and or destinations. And the register addresses are specified within the instruction word. Our immediate uses the 16 or 26-bit, depending on if it's an R or an I type or a J type instruction. And then register indirect obtains operand memory address from processor register value and the immediate 16-bit offset stored in the instruction word. We had 3 instruction formats, kind of 4. The R type is essentially the same as our E key, the only difference being when we had the opcode is 1F and the type of instruction was determined by the function code for our enhanced types. Then we have the I type, which has a 16-bit immediate, and J type, which has a 26-bit immediate, which is going to calculate the jump address.
So for our base enhancements required, we have input and output, which are basically implemented the exact same way as load and store, but access the I/O memory instead of the data memory. And then we have the return from interrupt instruction, which is based on a previous stack-based interrupt service routine call in which the program counter was stored onto memory, and then the flags, or the 4 ALU flags present state from the control unit concatenated with 28 bits of 0 into the memory. And our other 2 enhancements were push, which used a pre-increment with the function space having 0, 0, and pop, which is post-decrement, using 0, 1. In our implementation, it does have that problem where it runs over into the beginning of our memory because we are only using 12 bits, but we didn't discover that because none of our verification modules
failed.
Checked that
Yeah.
because it worked. Next, we're going to look at our hardware schematics, starting with the CPU test bench top level, which implements our MIPS CPU, our I/O module, and data memory. Both I/O memory and data memory use the same address bus, data in or data out bus, and data in buses, and each have three status or control signals: chip select, memory write enable, and read enable. And then the I/O module also has its own, or has a interrupt request from the CPU and an acknowledge, which is pointing the wrong direction, from the, a request from the I/O module to the CPU. That one's pointing the wrong direction, and an acknowledge from the CPU to the I/O module. In hindsight, we could have only used one write and read signal and had them both connected to the data and I/O modules, because the chip select's the one that could have been selecting the chips. And then the clock and reset only to the CPU. Now inside of the CPU, we have the control unit implemented, the instruction unit, and the integer data path. Starting with the control signals outputs to the memory over here on the left, and then the control signal or control units control signals to the instruction memory, four of which control the loading of instructions to the IR register or instruction register, and then three of which control the changing of the program counter. And then it also gets inputs from the integer data path in the form of ALU out for when we're doing a jump instruction, and outputs the program counter directly for certain branch instructions, and then, or not, yeah, no. Okay, and also 16 bits of immediate data, which is sign extended to 32 bits, and then the IR output is sectioned off into the destination address, the first operand address, S address, the second operand, T address, and a shift amount section. And then the entire 32 bits is taken by the control unit and IR in. And then the control unit has its outputs, or inputs from, or flag inputs from the integer data path, a function select to the integer data path to control the ALU, a flags out register, which is when we're sending the registered flag bits to be stored in memory, and then the our control signals for the data path's operation itself. The only change from normal here is the SA select, which is used for our push and pop instructions. Yes. And then inside the integer data path, we have the register file with inputs from the instruction register and selects from the control unit. We've adjusted the DA, or destination address mux, to include the stack pointer itself and the return address for jump and link. And then we added the SA mux, S address mux, to include the stack pointer directly for our stack instructions. And then down here we have the flags input from the control unit, and here's the concatenation of zeros for when it's being stored by our interrupt call. And then we have our data inputs from the I/O memory and data memory over here being registered, and then our YMUX, which controls the outputs of memory and data to the register file, or memory addresses and data to the memory or register file, and then over here our data out for the memories is there, and our flags for to the control unit. And next we have our ALU inside of that, which implements a MIPS control unit, or a MIPS unit, which does most of our calculations for our general instructions, and then a barrel shifter for shifting of instructions, a divider for division, multiplier for multiplication, and then a series of muxes to select between those, along with a series of muxes to select the appropriate set status outputs for 0, negative, carry, and overflow bits. And then our inputs are the function select, our two datas, and our shift amount just for the shift. Okay, next we're going to talk about how that operates on a per clock basis.
Alright, so this is just kind of a general overview of like the way each state works. So we have fetch, decode, execute, and write back. And this, some of the instructions will have more, some of them will have less for like a jump. But this is basically, most of the instructions are going to have a similar format to this. So this is an example for an R-type instruction for our add. In our fetch state, the instruction register is going to get the memory stored at the current location of PC, and the program counter is going to be incremented. And then in decode, RS and RT are going to be put in the registers determined by the address that's in the instruction. And then in our add state, based on the instruction, because it's an add, the ALU will get that function select for add. And then in the last state, the output of the ALU will be written back to the register RD. This is an example for an I-type. Same thing happens in fetch. In decode, it's a little bit different because we're going to get the sign extended 16-bit is going to go into RT and RS, and then for the add, the function select to the ALU is going to be essentially the same. And then in the last state, the register that's specified by the RT is going to be the destination, because for a I-type, there's no RD location. And then this is for the J-type instructions. In our fetch, same thing happens. Decode, nothing happens because there's no registers, and then the jump will occur in the third state, and PC will be written with the most significant 4 bits of PC plus the 26-bit, which is concatenated with 2 zeros for the jump address.
And then for our stack instructions, we're going to start off with our push. Fetch happens, decode only needs to obtain the stack pointer to RS, which is assisted by that mux we added. And then in the first state of push, our RTU registers, or our register files gets read at address RT into RT. And then our ALU out gets the stack pointer incremented by 4. And then on the last state, we write to our memory, which using the address from ALU out, which has been incremented by 4, and writing RT, which has our RT data. And then we also write back to our stack pointer the incremented value for the next step. And then for the pop, similarly, we fetch, decode only needs to load the stack pointer into RS. Our first stage loads ALU out with our stack pointer because we're doing a post decrement on this one. RD, in the next stage, RD, our input register is loaded with data memory at the specified ALU output by stack pointer, and then RS loads the stack pointer again so that on the next stage we can, after writing the input data to our destination register, have our stack pointer decremented, and then on the last stage we write it back to the stack pointer, the new decremented value. And now for our interrupt service routine call, assuming that the interrupt enable flag has been set previously using a SETI instruction, on fetch now, since we don't need to fetch our instruction word, we can immediately load the stack pointer into RS, and then on our first stage, skipping the decode stage and jumping in directly, we can now load our ALU out with our incremented 4 because of our pre-increment incremented stack pointer, and load the program counter into RT, and then on the next stage write to the memory at our pre-incremented stack pointer value, write our program counter, and then also store our incremented value to the stack pointer, and then on the next state read again our incremented value, and that way we can increment it again now by 8 and store our or store our flag input from the control unit into RT so that we can then store RT into the memory at the specified location, which has now been incremented by 8 with our flags, and also store the ALU output, which is our stack pointer, incremented by 4 to our stack pointer for future pop and push instructions. And we load our ALU out with 3FC, the location of our interrupt service routine, and then on the next state we load the data memory location there, which will now be the memory address of our ISR, and then on the last state load that memory address or instruction memory address into the program counter and set our interrupt enable bit to 1, which will then be turned off immediately afterwards in our next instruction.
Could you go back to the first set where you had fetch? Is that right there? Yeah. You say you're going to read the stack pointer in fetch. Do you always read that in fetch?
No, just when we've gotten an interrupt
So you conditionally read it in fetch? You've got an if statement or something?
in fetch, yes.
So you do have an if statement related to RS being loaded?
Related to the interrupt being on, or the interrupt request being on and the interrupt enable being enabled.
So
both of
if
those
that's
are
true,
enabled,
you're going to do that?
we're going to do that first.
Okay. So that was a little modification.
Yes, to save 1 state.
Okay.
Because nothing else needs to happen in fetch, because we're not loading an instruction word.
Alright, so now we're just going to do like a little bit about the verification instructions from IMEM1, IMEM13, and then our instruction memory that Jared wrote for push and pop.
Good.
So for IMEM1, this was just a test of branch equals and the branch not equals. And so the things we're looking for here are the 2 pass flags, which is clearing R15 and R14, and that there was a store to memory at R13. And as you can see from up here, we have all of those, and at the data memory location of R13, we have R1 stored. For the instruction memory 13, this was a test of the input and the output, and it also tested our barrel shifter. So what we have here is we have a loop where the value of R17 is being stored at the IO memory location specified by 16, and then after that it's shifted right arithmetically twice. And so you can see when we have it stored at the IO memory that the sign bit is staying the same in each. And you can see that because the shift right arithmetic occurs after the output, our final value of register 17 is going to be FFFF, because there's an additional shift, so
Right.
that it'll shift in the sign bit, so it'll be all ones. And then we also have the input, so on registers 19 through 24, we can see that at the different memory location, IO memory locations of R16, that we're getting the same corresponding as what's stored in there.
Right.
And then this was what we wrote for this is what Jared wrote for the push and pop. So we basically have a Louis Ori, which is for registers 1 through 3, and that's just loading in base values to be pushed onto the stack. Then we did 3 pushes and 3 pops, and after each push and pop, we stored the value of the stack pointer at registers 17 through 22. So you can see that it's being incremented and decremented. And one thing that we noticed is because it is it's being added, that the memory location isn't actually at 400, it would be at 0.
Mm-hmm.
And then you can see, because stack is the last in, first out, the first thing that's popped off the stack is the last thing that was pushed onto the stack there. And then that's pretty much it. Some planned enhancements that we had. We wanted to do SIMD and pipelining. We did a little bit on pipelining, but not that much, and more just the higher level thought about what we would do for SIMD. But when it came down to actually implementing stuff and getting this done, we realized that we weren't going to have enough time. Some other instructions we thought about were like a clear or clear flags, but we realized that those wouldn't be the best because we already have other instructions that can do the same thing. Thank you very much.
Excellent.